So this is the next topics. These topics talk about combinational circuits or typical combination circuits. Circuits here refer to digital electronic circuits. The things that I'm going to cover in these topics, the first one is on half adder, and then the full adder, decoder, comparator, and then multiplexer. So these are the things, or these are the typical circuits that used in combinational digital electronic circuits that I'm going to discuss in this particular topic. A link to your learning outcome. So one of your learning outcome is to be able to apply digital logics to system applications. So what I hope you get out from this is to know how to use this sort of combinational digital logic circuits to design simple system. So means that the simple system itself, for example, a full adder can be considered as a simple system. So if you know the circuits, how to design a simple full adder using digital gates that consider a combinational logic circuits to achieve a system in this sense. Or in a more standard systems, so you can make use of the adder itself to build a larger binary additions, for example. So to go back to what we have learned about numbering systems in the earlier topics, so we talk about two complements number. So we start off with a one complement. So in one complement, if we have a string of binary numbers, to convert that into one complement, we inverse all the bits. So if you have a 0, they become 1. And if it's 1, it becomes 0. So to do that using digital circuits, I'm sure you have figured that out. In order to invert the bits, we just simply put it through an inverter or a NOT gate. So if we fit each of these bits stream through an inverter or a NOT gate, we achieve a one complement. And then to achieve a two complement, we have to add 1 to the less significant bits. Okay, so that is how you can achieve the two complements. Okay, so from one complement, you add 1. And therefore you achieve your two complements. So the two complement itself is used as a signed binary number. Okay, so for example, if we have a negative 58, we can use a two complement number to represent the negative number. So we use the most significant bit. So in this case here is the 8 bit. So the 8th bit is used as a sign bit. And then the 7 bit itself is used as the magnitudes of the bits. So earlier on, I mentioned that to work out, if it's a signed binary number, to work out what value it is, you can convert this again in two complements. You find that it will be equals to a positive 58. So meaning that if you have a signed bit as 1, if you do two complements again, the signed bit becomes 0, and the value of that binary number will be equals to 58, and that tells you that this is a negative 58 numbers. Another way of doing it is we can assign the 8-bit. Okay, so although we said the 8-bit is used as the signed bit, so we'll use the 8-bit as minus 128 for an 8-bit system. So this is a negative 2 to the 7th, and it gives you minus 128. And we can work out this negative number by summing all the values of each of the bits. And the 8th bit is assigned a value of minus 128. So instead of the normal binary, if you have an 8-bit binary number, then the 8th bit will be just 128. But if it's a signed binary, we assign the 8-bit as minus 128. You'll see in a minute why we'll do that. Okay, taking our example just now, the minus 58 number, so which is a two complements signed number. So if we assign the 8-bit, so 8-bit is 1, so we assign that bit with the value of minus 128. And then all the bits that is 1, we assign their corresponding binary value. So for example, bit 7 will be 2 to the 6, which has a value of 64. So we assign a positive 64 to that value. And then we have here a bit at the 3rd bit, which is 2 to the power of 2, which has a value of 4. And we assigned a positive 4. And then the 2nd bit is 2. So if we sum all this value, okay, so you have 64 plus 4, which is the 68. 68 plus 2, that will be 70. And then we take that value, sum it with minus 128, we get minus 58. And that is our equivalence of our two complements signed number of this 8-bit binary value. Okay, so this is another way of working out the value of a two complements number. And you can go ahead and do two complements again on this value. And you can see that that will also be equals to positive 58. And the sign bit tells you that it is negative. So you can also do that to work out its value. Okay, so this is just the working of that example. I'm not going to repeat that again. So we talk about signed binary number. So why do we use two complements? The idea is that we want to do subtractions in binary number. So if you want to take, for example, 60 minus 58, and we know that this simple arithmetics will be equals to 2. So if you take 60 minus 58, we know that that's equals to 2. But in digital circuits, we are not able to do subtractions. So we can't do minus binary number in digital circuits. So in order to perform these mathematical operations, so we convert this into an addition. So instead of doing 60 subtract 58, we take 60 to a negative number. So if we can convert 58 into a minus 58 number, then we can do additions. And that's equals to 2. So that is where we need a signed binary number. And the signed binary number that can work in this example is to use a two complements system. This is an example to illustrate how it can be done to add 60 with a negative 58, or doing 60 subtract 58. Although in our mind, these two are the same thing, but from the circuit point of view, this is totally different, because having it as a negative number, the operations that we're performing is an addition, whereas in here, we're trying to perform an operation which is subtraction, and that is not able to be performed in digital circuits. Here, you can show that your simple binary additions. And if you add this, so 0, 0, add to 0, 0, 1, add to 1, 1, 1, add to 1, 0, and 1 will be the carryover. So we have, so here 1, 1 gives you 1, 0. So we have a carry. And then the carry add to 1 can give us 1, 0. Again, you have another carry. And 1, 0 again. So 1, 1 add to 1, 0. Again, another carry. And then 1, 0, and a carry. And then 1, 1, again, 1, 0. And then 1, 1, 1, 0. So we end up with, so we start off with 8 bits. And the sum of this end up with a 90 bit. And we will discuss this 9 bit. And you can see that the 8 bits now becomes 0. So this indicates that this is a positive number. This show is a positive, and this show this is a negative. And then our sum here ends up with a 0, which is a positive values. And then if we convert that back into our decimal, you can see that this 8-bit signed binary number is equivalent to 2. So this is tally out with what we understand about addition. So 60 add to minus 58 gives us 2. And this is how we can achieve subtraction in digital circuits or in digital logic circuits. Okay, so that leads us to binary addition. So if you want to add two binary stream. So in this case here, it's a 4-bit binary. So simple additions. So we have 0, 1, 1, 0 at 0, 0, 0, 1. This is to illustrate our two complements. So we can do one complement using the inverter, and then we need to add 1 to make it into two complements. So if we add 1, so this is just your normal addition. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 0 is 1. And then 0, 0 to 0. Okay, so this is just very simple binary additions. So this is the first case. Second case. So if we have 0, 1, 1, 1, if we add 1, so now 1 plus 1 is 2. In binary, 2 is 1, 0. So we have 0, and then the 1 is the next bit. It's a carry. So in our normal additions, we'll carry over to the next columns. So this is top here is our carry bit, and here is our sum bit. So 1 plus 1 gives us 1, 0. So 0 is the sum bit, and the 1 here will be our carry bits. And that carry bit will be add on to the next column. So here we have again 1 plus 1 gives us 1, 0. Again, we have the sum is 0, and then we carry 1 bit over to the next column, and so forth. Okay, so this illustrates that this is two scenario in binary additions. So in this case here, we don't have carry, very simple. 0 plus 1 gives you 1, 1 plus 0 gives you 1. And here we have exceeding the value, so we have to carry over 1 bit to the next column. So here we have the top row, we call it X. The second row, we call it Y. And then we call this row as the sum. And the top row, the carry over here, we call it C. So what we have is that we have Xn. N is the index of our binary bits. So if we call this bit 0, this will be bit 1, bit 2, and then bit 3. So to refer to this bits here, call this Y0, and this bit here will be X0. Or this bit here will be the sum 0, 1, 2. So this is S2, for example. Okay, that's how we index up all our variables in this 4-bit addition. So putting that in terms of the variable, instead of writing as our 1 and 0, our additions can be written as, so we have our X variable that has X3, X2, X1, X0. So X0 is the least significant bit, and bit 3 is the most significant bit. And to do the additions, so X0 plus X, so X0 plus Y0 will give us 2 bits. Okay, so we have x0 plus y0 will give us a c0 and s0. So the c0 need to be carried over to the next column. So c0 will show up here, which is the outputs of this operation. So x0 plus y0 outputs 2 bits. One bit is s0, which is the sum, and c0 is the carry. And that carry will be fit into the next column. And that the next bit here is another different operation. So we concentrate on this column bit 0 for now. So we'll look at this here. So we want to do an addition of x0 plus y0. And we know that from our previous example here, we know that there are two possibilities. There can be either just a single bit. So 0 plus 1 gives us 1, so this is just 1 bit. But it can also end up with 2 bits. So if we have 1 plus 1, we end up with 1, 0. 2-bit additions can end up with 2 outputs. So this is how we represent them. So x0 plus y0 is equals to c0 and s0. So 2 output variables. So this leads us to a system, what we call a half adder. So we're summing bit x0 and y0. And then we have 2 outputs. One is the sum, which I call Sn, and then the carry is Cn. Okay, so we can write down in our truth table. So 0 plus 0, so the sum is 0. 0 plus 1, the sum is 1, there's no carry. And 1 plus 0, the sum is 1, and then there is no carry. And then 1 plus 1, the sum is 0, and then you have 1 carry. Yeah, the way it's presented here is a bit misleading. So if we swap the 2 columns, x, y, then you can see it more clearly in terms of the normal binary addition. If I put my carry here and my sum here, so it will be 0, 0, there will be 0, 0. 0 plus 1 gives us 0, 1. 1 plus 0 gives us 0, 1. And 1 plus 1 gives us 1, 0. Okay, so this is our normal binary addition. And here is just swap these 2 columns. From this truth table, so if you look at this sum columns, you can see that 0, 0 gives us 0, 0, 1 gives us 1, 1, 0 gives us 1, and then 1, 1 gives us 0. So going back to your basic logic gate truth table, I'm sure you can identify this truth table is an XOR function. So we can perform our sum outputs using an XOR gate. And then if you look at the carry columns, you can see that this is a 2-variable AND gate. So meaning is that if I were to write down these expressions, the sum will be x bar y, or with x, y bar. And then the carry is simply x, n with y. So that's just a simple AND gate operation. And this is a simple exclusive OR functions. Okay, so we know this, so we can build this circuit very easily. So this is simply our XOR, and then this is our AND. So our two variable inputs, our X and Y, put that to our XOR gate that will get us our sum, and then put it through an AND gate that will give us our carry. And we can write this circuit, or this digital circuit, can be combined into a block, something like this: two inputs, X, Y, and then two outputs. One is the sum, and the other one is carry. Okay, so the sum here, and then the carry. So we call this output, so we call it Cout. And this block diagram, or this circuit, is called a half adder. Okay, so this is one simple system. So we have a combination of logic gate give us a small simple system that perform half adder. So we'll look at in a minute why this is called half, and we have a full adder in the next couple of slides. Using a simple block here with these two inputs, two outputs, we can represent these circuits here. So you can either build this circuit with logic gate, or you can actually get a chip that actually do the same thing. So instead of building this using logic gate, you can find a half adder chip, just like your gates, your AND gates or OR gate chip that you use in the lab. Full adder. If you consider the next bit, so when we discuss about a half adder, we discussing about the very first bit in the additions. We're talking about the bit 0. Now we're going to look at something called a full adder. We're going to discuss using the bit 1. So if we go back to our example, so just now when we do our half adder, so if we add X0 with Y0, we end up with 2 bits. One is the sum bit, one is the carry. We know that in normal mathematical calculations, this carry is included in the next column additions. So our Cout 0 here will become an input to the next bit's calculations. So we have a Cout 0 here, and this become an input to the next bit. So I put it Cin 1 because this is now we're doing our bit 1 calculations. So this bit here, just now we do, this is a half adder. And now this bit here, we're going to look at this bit, and we call this a full adder. I'm not sure whether you have identified the difference between them, but I can simply illustrate this. In here, we only have 2 inputs. x0 and y0. Although in our binary number, we still have two inputs, x1, y1 in this bit 1 calculations, but we have an additional inputs that give rise from the previous calculations. So now we have three inputs into our system. We need to add 3 bits. So we need to add x1, y1 with c in 1. And c in 1 could be 0 or 1 depending on bit 0 addition. So we're now doing 3 bits binary additions, not 2. And this is what we call a full adder. And the half adder, we do not have a carry bit to consider, and therefore it's only 2 bits addition. So 2 inputs give you 2 outputs. But here we have 3 inputs, but again, going to give us 2 outputs. So we still have the sum and the carry. So if you look at the bit 1 columns, so we still have our x and y, and x and y can be 0 and 1. And then we have another input, which is c in, which is a carry in from previous calculation, carry out from our half adder, for example. And the output of this, again, we have the sum and a carry out as well. So we can go through our simple calculation, addition, or going through our truth table. So again, when we have 3 variables, we want to list them in a proper order, going from 0 to 7 in the 3 variable. Okay, so this is going from 0, 1, 2, 3, 4, 5, 6, 7. So if you list them in this way, you will have list all the possibility of these 3 variables. The other things that I point out to some students in the lab when they write down the truth table, sometimes they don't arrange it in the right order. And I mentioned that if you look at these distributions, you can see that there is a clear pattern in the way how going from 0 to 7. So if you look at the least significant bits, it's go from 0, 1, 0, 1. So it's keep alternating every bit. And the next column go from 0, 0, 1, 1, 0, 0, 1, 1. And then the next one, we go 4, 0, 4, 1. And if you have a 4th column, this whole thing, you're going to repeat down here, and then you get 8, 0, 8, 1. And then it carry on if you have more variables. So there's a distinct patterns in this, and you can easily check whether you have listed them down correctly by looking at these patterns. So you're going 0, 1, 0, 1, 0, 1, and this goes 0, 0, 1, 1, 0, 0, 1, 1, and then here go 4, 0, 4, 1, and then the next column will be 8, 0, 8, 1, and the next one will be 16, 0, 16, 1, and so forth, if you have more variables. Okay, so this is how you can check, very easily check, whether you have list down or your possibility of the variable in the truth table. Okay, having said that, let's go back to what we're discussing. So we're going to do additions of x, y, and c in. So we're going to sum for this column. So 0 plus 0 plus 0, the sum will be 0, the carry will be 0. 0 plus 0 plus 1, sum is 1, no carry. 0 plus 1 plus 0, again, sum is 1, no carry. And then we have 0 plus 1 plus 1. This is equals to 1, 0. So we have the sum 0, 1 carry over. Then 1 plus 0 plus 0. Again, the sum is 1, no carry. 1 plus 0 plus 1. Again, sum is 0, carry is 1. So this is 1 plus 1 is 1, 0. And then 1 plus 1 plus 0. So again, 1, 0. The sum is 0, the carry is 1. And then we have 1 plus 1 plus 1. There's 3. 3 in binary is 1, 1. So we have a sum of 1 and a carry of 1. Okay, so this is our truth table. So again, we have 2 outputs, the sum and the carry. And now we have 3 inputs. So we have a truth table, 3 variable truth table. We can put it into CAMAPs and minimize the functions. So we look at so this is the carry. So 0, 0. Okay, so this is 0, 1, 2, 3, 4, 5, 6, 7. So this is 0, 1, 2, 3, 4, 5, 6, 7. Okay, so 0, 0, 0, 0. And then here at 2, that is 0. At 3, got a 1, so I put 1 there. At 4, got 0, you put 0 there. At 5, you got a 1, and then 6, you got a 1, and then 7, you got a 1. Okay, that's how you can put it into a CAMAP. And then next, we want to group 1. So in this case, we can group a group of or a pair of 1. So there's no group of 4 of 1s in this CAMAP. So in this case, we can regroup in pairs. So here we can see that there's 1 pair here. So we've got 1 loop here. We got a pair here. So we draw another loop here. And then we got a pair here. We draw another loop here. So this loop here, okay, we got 1, 1. So in this loop here, we can see that Cin changes. So we only have XY in this product term. And then in this loop, X change. So we're looking at this loop here. So C in not changing. So we have our X change. So going from 0 to 1. So Y stay the same. So we have Y and C in. And then the next loop, this loop here, again C in not changing. And then we're looking at now we're looking at this combinations here. And now we see that 1 in Y changes to 0. So we can eliminate Y. And X stay the same. So now we have these terms here, X, C in. So this is our carry out columns. So we have an expression for that. So I'm sure you know how to build a digital combination circuit for that function. Okay, so we start off with that functions here from our care map. And here is just a bit more manipulations using our Boolean algebra law. We can show that this expression can also be written as x n with y, or with c in n with x exclusive or with y. Okay, so I'm not going to go through this, but you can look at this at your own time to convince yourself this is the case. The reasons why we want to do that will be apparent in the next few slides. And then we're going to look at the next column, which is the sum. And here, again, from the truth table to our care map, we can write down the K map for the sum functions. So we have, again, 0, 1, 2, 3, 4, 5, 6, 7. So this goes 0, 1, 2, 3, 4, 5, 6, 7. So we got 0, 0, and then 1 here. And then at 2, we got a 1. At 3, we got a 0. 4, we got a 1. So there's an error here. So we should have a 1 here. And then 7, we got a 1. Okay, so our sum care map of 0, 1, 1, 0, 0, 1, 1, 0. In this care map, you can't draw any group of 1. Okay, so the 1 is all over the place, and you can't actually group them. So you cannot simplify this function. Okay, so this is the sum. So to achieve our full adder, we can use 2 half adder and to achieve this full adder. Okay, so this, if you write down these expressions, you can see that this is actually equals to x exclusive OR with y, and then exclusive OR with cin, which is these functions here. And if we build our full adder using half adder, so our half adder, we have 2 inputs, 2 outputs, and the outputs of the sum is an exclusive OR of the 2 inputs, and then the output of the carry is just an AND of our 2 inputs. Okay, remember that our half adder circuit, you have this. This is our sum. This is our carry out. This is x exclusive OR with y, and then this is x and with y. So here, I just change the inputs to A and B, just to differentiate it from the x and y of a block diagram. So the output, if the input is A and B, then the sum output will be A exclusive OR B, and then the carry will be A and with B. And this outputs, the sum outputs is fit into the X of the next adder, and then the carry is put through an OR gate with the outputs carry from the second half adder. And the third input, which is carry in, and that fits to the Y of the second half adder. So the outputs of this, the second half adder, the sum, will be this function here, exclusive OR with this inputs. Okay, so this will be this outputs. A and B come from here, and then C is the inputs of this my inputs to my half adder. Okay, so this X, if I call this X2, Y2, so this is X2, Y2. So X2 is our A exclusive OR with B, and then Y2 will be our C in. And this gives us the outputs of A exclusive OR with B exclusive OR with C in. And that will be of these functions here, which is the sum of a full adder. And then the carry out, if you look at the output from the carry out from the first adder, so this is AB, and then here C out will be my X2 and with my Y2. And therefore this is all with the C out of the first adder. So the output of C out here is AB, and Y2 is, no, sorry, X2 is A exclusive OR with B, and then Y2 is C in. And then we have an OR gate here, meaning that we OR these functions with A and B, and that will be our carry out functions of our full adder. So what we have here is we have three inputs, A, B, and C in, and then we have our two outputs, which is the sum and the carry out. Okay, so that is our full adder circuit. So what we have done so far, we have looked at a half adder and a full adder. So the difference between the half adder and the full adder, the half adder only adding 2 bits without considering any carry bits, whereas a full adder, although you're adding 2 bits, but you will consider a carry bits from the previous calculations. So if you want to add 3 bits number, so this is how we can build up our system using half adder and full adder. Okay, so for our bit 0, and this for our bit 1, and this for our bit 2. We have 3 bits to add. Okay, so for the 0 bit, we do not need to consider the carry bit, so we can use a half adder here. So we have two inputs, X naught, Y naught, and then we have our sum and carry. And this carry bits from the first bit calculations need to be fit to the second bit calculations or bit 1 calculation. So we tie the C out of the half adder to the C in of our full adder. Okay, so and then we have our bit 1 from our X variable and bit 1 from our Y variable to be added to the carry bit from the bit 0 calculations. And then we have our bit 2 here, and our output will be our S0, S1, S0, and this is the carry bit here will be our 4th bit. So we're adding 3 bits to 3 bits, and there is a possibility of ending up with 4 bits binary number. Okay, so that is how a simple example of how you can make use of a half adder and full adder to build a simple bit additions, or in this case here 3 bits additions.